In this video, we will talk about how to find the area between curves when our curves are functions of y. So what does that mean? Let's draw a picture. So let's say that we have our axes, and when our curve can be described as a function of y, let me give an example. For example, that's something like x equals y squared. So we are writing x as in terms of y, or x is a function of y. And x equals y squared, just remember from algebra, you may have seen this. This is a sideways parabola. A sideways parabola. Okay, so I'm going to draw a picture where my curves are now going to be functions of y. They're going to be written so that you have x equals something with y's in it. So when that happens, our functions graphically sort of appear to be kind of sideways-ish. Okay, so maybe I have one function that looks like this. And I'm going to call this x equals f of y. And I'm going to draw another function. And let's call this one x equals g of y. And I'm going to be interested in finding the area between these curves over some interval along the y-axis. So if I were to draw a picture, dotted lines here too, we'd want the area over the interval from c to d between these two curves. Okay, so we are going to derive a formula for this like we did in a previous video by splitting this up into rectangles, although I'm just going to do it a little bit more quickly than we did it before because we've seen it one time already now. Okay, so I could split this up into some rectangles, so I will have some rectangles here. Okay, and I'm going to use this point to be sort of the left part of this rectangle, and this point to be sort of the right end of that rectangle. And then I'll draw another line, and then draw a rectangle, and then that. Okay, and then I could keep going like this and drawing rectangles. But somewhere further up along the road, I'm going to draw an arbitrary sort of rectangle. So I'll draw a line like this, and then draw the right edge of it, and draw the left edge of it, and then have my rectangle like that. So with this rectangle, I'd like to be able to describe its area. So this sort of vertical width is going to be a change in y now instead of a change in x as it was before, because this is a vertical distance. And then I need to know sort of the horizontal length of this. And for the horizontal length, what I'm going to need to know is, at these sample points, what is the y value? I'm going to call this yi. Remember before in my picture, this was x sub I when these were functions of x in our previous video. And then what I would need to do is, I would need to plug in whatever this y value is, yi, into the function f of y, and then plug it into g to know g of yi, subtract those, and that is how wide this would be. It would be f of yi minus g of yi, and now we are ready to write down the area. So for this area, I'll sort of begin by writing the area of this arbitrary rectangle here, which is f of y sub I minus g of y sub I. That's sort of the length. And then I multiply that by this height, delta y. And that would be the area of just one of those rectangles. Now, if I wanted to sum up the areas of n rectangles, I need to put a sigma in front of this and say, okay, let's let I go from 1 to n. So I equals 1 is talking about the first rectangle. I equals n would be talking about the nth rectangle. So far, this is still just an approximation for the area. If I want to make it exact, I need to let the n go to infinity. So I have to take the limit as n goes to infinity. And as we've seen before, this is going to be a definite integral. This is going to be an area. So, sorry, our area is the integral of f of y minus g of y. So the yi's change to a y when we go to the integral. the delta y becomes dy. And then looking at the picture, the interval for y here was from c to d. And that's going to be our formula for the area between curves when the picture looks like this. I'm going to introduce some notation here. F of y and g of y, instead of calling these the top function and the bottom function, I'm going to call f of y the right function. I'm going to call it x sub right, because our formula will typically look like something like x equals y squared, where you have x on one side and then expression with y's on the other side. Similarly, g of y, I'm going to call this x left. And you'll have to do the right x value minus the left x value and plug those in to this formula. Alrighty, so let's look at an example. Okay, so let's find the area between these two curves. So the first one is y squared equals x plus 1. The next one is x minus 2y equals 7. Okay, so it's going to be helpful if we can draw a rough picture. So I'm going to draw some axes. And looking at these equations, if I were to look at this y squared equals x plus 1 equation, I can isolate x and get that x equals y squared minus 1. And from that, I can tell that this is a sideways parabola. That's a sideways parabola. So x equals, if the minus 1 wasn't there, it would just look like that if the minus 1 wasn't there. What the minus 1 is going to do is it's going to make the x value, it's going to make what x equals one unit smaller. Because before, this graph was just x equals y squared. So when we do x equals y squared minus 1, it's making all the x coordinates 1 unit smaller. So that's going to shift everything to the left by 1 unit. So it's going to make the parabola look like this. Okay, so we have a parabola that looks like that. And then x minus 2y equals 7. Hopefully we can recognize that this is a line. It might be helpful to isolate the y actually first to get the y-intercept and the slope of this line. So rearranging the terms, we'll get x minus 7 equals 2y. And if I divide by 2, we'll get 1/2 x minus 7 halves. Oops, 1/2 x minus 7 halves equals y. And from that, I can tell what the slope and the y-intercept of this line are. Okay, so in terms of graphing that line, it's helpful to know what the intercepts of this parabola are. So from the shift, we can see that this x-intercept is at -1. The y-intercepts for the parabola we could find by setting x equal to 0. And if you were to set x equal to 0, we'd end up getting y equals plus or minus 1. So this is at 1, this is at -1. So I can see with my line, the y-intercept needs to be smaller. The y-intercept is -7 halves. And the slope is positive, which means my line is going to look something like, I'm going to exaggerate the picture. It's going to look something like this. I'm exaggerating it and making it a little bit steeper than it actually is to make sure that I can see that it's going to cross twice. Okay, so in this line equation, let's also isolate x. Whoops. In the line equation, if we were to isolate the x, we'd get x equals 2y plus 7. And that's going to be my right function. And in the parabola equation, we had already isolated the x. We got x equals y squared minus 1. And that's the left function. Okay, so what we need to know still is what are the intersection points. I need to know these intersection points, that one and this one, so I can figure out the interval, my limits of integration. All right, so let's find those intersection points. Intersection points. So we have these two equations. We have x equals y squared minus 1, and we have x equals 2y plus 7. So let's set them equal. We're setting those x's equal. Set y squared minus 1 equal to 2y plus 7. And now I can rearrange this to get all the terms on one side. We get y squared minus 2y minus 8 equals 0. And this is easy to factor. Let's see, this factors as y minus 4 times y plus 2, and then equals 0. And now I can say what y equals 4, and y equals negative 2. So let's take these y values, and at this point, I don't need to figure out what their x coordinates are. I can actually just write my integral at this point. But later in this video, I'm going to show, well, what would this have looked like if I didn't do this in terms of a right function and a left function? What if I did it in terms of a top function and a bottom function? And for that, it's going to be helpful to know the x coordinates. So I'm going to find those now. Okay, so if I take this y value, y equals 4, I could plug it into either one of these equations to get the x coordinate, because they're supposed to intersect at this point. So the x coordinates should be the same at this y value. So if I just plug it into 4 squared minus 1, we get 15. If I do the same thing with the other y coordinate, negative 2, we'll get negative 2 squared minus 1, which is 3. So let's label those in the picture. Alrighty, so here's the picture one more time. And this top intersection point is 4, 15. And the bottom one is 3, negative 2. Okay, so we are ready to set up our integral now for this area. Okay, so I just shifted the screen back to where I was writing before. So I'm going to talk about how to do this in two ways. So first, I'll call this solution 1. Solution 1 is going to be to do this as a dy integral, which means I'm going to think about it in terms of my right function and my left function. So the area is going to be an integral. The limits of integration, these bounds, will be y values rather than x values. And what y goes from is from negative 2 to 4. And then I need to write down what my x right would be, and then minus my x left. And this is going to be a dy integral now, because the x right and x left are going to be functions of y. They're going to be in terms of y. So this has got to be a dy integral. All right, so we have integral from negative 2 to 4. And my right function was the line. What was x equal to there? It was equal to 2y plus 7. Then I got to subtract what x left is. So let's put a parenthesis around it so I don't forget to distribute that negative sign. And the left function was the parabola equation. And that was x equals y squared minus 1. And I got dy. So from here, I just simplify, take the antiderivative. So negative 2 to 4. When I distribute the negative, I'll get negative y squared. We'll still have the 2y. And I'll get 7 plus 1, which is plus 8. So now we are ready to take this antiderivative. So evaluating this antiderivative, we get negative y cubed over 3 plus y squared plus 8y. And now we got to plug in 4 and negative 2 into this. Okay, so plugging in 4, we will get negative 64 over 3 plus y squared will give me 16. And then plus 8 times 4 is 32. And then minus what you get if you plug in negative 2. So plugging in negative 2 to the first term, we will get positive 8/3. Into the next term, we will get plus 4. And then 8 times negative 2 will be negative 16. Awesome, okay. So we just need to continue to simplify. So let's first combine these terms that have a 3 as the denominator. So we'll get negative 64/3 minus 8/3, which is negative 72/3. And then these other terms will give me, so 16 plus 32, that's 48. And then the 4 minus 16 is negative 12. So altogether we have 48 plus 12, which will give me plus 60. Alrighty, and then negative 72 over 3 is negative 24. We get negative 24 plus 60, which is 36. And that's my area. That's my area between those two curves. Okay, but I want to talk a little bit about well, what would this look like if I hadn't done this way? What if I had done this as a dx integral in the first way that we learned how to do it? Okay, so here is what my picture would look like. Okay, so I'm just going to shift that up a little bit because I had a little bit of extra room there. Okay, so take a few seconds if you need to copy this into your notes, but it's the same picture that I had before. Alrighty, let's talk about this. So dx integral just means I'm going to do it in the first way that we learned how to do it before this video. I got to think about my top function, and I got to think about my bottom function. So what I want you to do now is pause the video for 1 minute just to think about what is my top function and what is the bottom function. So 4, 3, 2, 1, pause that video. Pause it for 1 minute to identify what the top function and the bottom function are. All right, so hopefully you did that. Hopefully you paused it for about a minute to think about what those would be. So with this question, it's a little bit more, it's not super straightforward what the top and bottom functions are because they switch somewhere. In fact, at this intersection point, 3, -2, if I draw a dashed line, it splits up the region into 2 pieces. I'm going to call the one on the left A1, and I'll call the one on the right, A2. And for A2, I can see that the top function is this parabola, and the bottom function is the line. But for A1, the top function and the bottom function are both the parabola. And that's a little bit weird. Okay, so here's one thing that I know that we'll need to do at some point if we're going to do the area this way, which is we're going to need to know what y top and y bottom are. So we need to isolate y in each equation. So in the line equation, x equals 2y plus 7. Let's see, if we isolated y, we would move the 7 over and get x minus 7 equals 2y. And then dividing by 2, we would get y equals 1/2 x minus 7/2. And that's the line equation when y is isolated. Now if we do it for the parabola, x equals y squared minus 1, I can move that 1 over and get x plus 1 equals y squared. And then square root both sides to get y equals, and anytime I even root both sides of an equation, I got to put a plus or minus. We get plus or minus square root of x plus 1. So that gives us 2 possibilities. Y equals a positive square root and y equals a negative square root. And we've reviewed what the difference of these is, what the difference between these is graphically when we talked about circles and semicircles. Okay, so y equals the positive square root of x minus 1 is going to be the top half of the sideways parabola, because the fact that we have a positive root means that the y values cannot be negative. So that's going to give us the top half. Similarly, y equals negative square root, that would just be the bottom half of the parabola. So from here, now that we've identified the top and bottom functions, we can set up the integral from here. And that is actually going to be a homework question to finish that off, the setup of the integral and working that out. But notice that doing it this way is just harder than doing it the first way, for a few reasons. One reason is, when we did it this dx way, we needed to split up the region into 2 pieces because the top and bottom functions changed at some point. In fact, actually in this one, just the bottom function changed. In area 2, the bottom function was the line, but in area 1, the bottom function was this negative square root function. So that made us need to use 2 regions. But when we did it in our first solution, using a dy integral, there was just one right function the whole way and one x left function the whole way. So we just needed one integral, and that made it easier to do. Finally, in terms of our goals for this section, we have done our last goal, which is discussing how to find the area between curves when our curves have the form x equals some stuff.